So our first question here is R2 a subspace of R3? Yes or no, or a trick question? What do you think? Trick question. Trick question is partially correct, in a sense. The true answer, if you had to say yes or no, is no. Why is R2 not a subspace of R3?
Incompatible type.
In a sense, they're incompatible types, is what was said here, and that's correct. R2 consists of all vectors with two components, column vectors say. R3 consists of all column vectors with three components. If you got two components, you don't have three components, right? R2 is not even a subset of R3, much less a subspace. R2 is not even a subset of R3 because vectors with two components don't have three components. But you might say, well, couldn't we just add a third component of 0? Is that what you're going to say?
Yeah, I was gonna say with R3, third component 0, then effectively not fit at all.
Yeah. So that's why it's partially a trick question too. It's almost a subspace, you might say. Well, yeah. If you want to be official about it, R2 is isomorphic to a subspace of R3. The plane, pretend this is the plane, R2. I'm drawing it as a square or a rectangle here, but imagine it goes on forever in all directions here. Is isomorphic to, we could use that kind of symbol, a subspace of R3. This is supposed to represent a picture of R3 here. Three-dimensional space. In fact, it's isomorphic to infinitely many subspaces of R3. The most natural one to pick is the XY plane here, sitting inside three-dimensional space. Take your vectors with two components, say A, B, and effectively map it to a vector with three components where the third component is 0. That would define what's called an isomorphism, a linear transformation that's one-to-one and onto, from R2 to R3, whose image would be the XY plane sitting inside three-dimensional space. But not all of R3, it's not an onto function. So R2 is not a subspace of R3 because it's not even a subset, but it is kind of a trick question. It's isomorphic to a subspace of R3. And again, in fact, infinitely many. Any plane through the origin is isomorphic to R2. There's infinitely many choices for what it's isomorphic to sitting inside R3, but this is the most natural one to think of. Is P2 a subspace of P3? All polynomials of degree less than or equal to 2, all polynomials of degree less than or equal to 3.
Yeah.
That one's yes, and it's not really a trick question. It is certainly a subset. Every polynomial with degree less than or equal to 2 is also a polynomial with degree less than or equal to 3, right? So this is definitely a subset of that. After that point, that doesn't prove it's a subspace, only that it's a subset. To prove it's a subspace, there's really essentially three things to verify. Anybody look up the subspace test? Remember what those three things are? 0, the 0 vector is in there, meaning in this case, the 0 polynomial, which is just 0, the function 0, whose graph is the horizontal line on the horizontal axis. 0 is a polynomial of degree less than or equal to 2, as well as a polynomial of degree less than or equal to 3. Real subtle technicality. Technically speaking, the 0 polynomial has an undefined degree, but we don't worry about that. Think of undefined as being less than or equal to any number, even though that's a nonsense statement. Don't worry about it. 0 is in here. It's definitely in there. What about closure under addition and scalar multiplication? Give me two polynomials, f of t and g of t in P2, Is there some in P2? Well, we already know there's some is definitely in P2 because P2 is a vector space to begin with. In fact, I really don't have to even use the subspace test here. It's enough to know that this is a subset of that and also know it is a vector space in its own right. But it is closed under addition. Give me two polynomials, f of t and g of t in here, meaning they have degree less than or equal to 2. Their sum is going to have degree less than or equal to 2. And give me a polynomial in P2. That symbol there means is an element of, and give me a scalar alpha, a real number. That scalar alpha times the polynomial f of t is definitely still in P2. Multiplying a polynomial by a scalar doesn't change its degree. Adding two polynomials with degree less than or equal to 2 doesn't increase its degree. Could decrease its degree if g of t is the additive inverse of f of t, like if f of t is t squared and g of t is negative t squared, then f of t plus g of t would be the zero polynomial. But it's not going to make its degree bigger. So yeah, you could use the subspace test, but you really, if you already know these things are both vector spaces in their own right, it's enough to know this is a subset of that to say it's a subspace. Subset just means every element in the first set is an element of the second. Subspace means more. It means it's a vector space in its own right. The zero vector, in this case, zero polynomials in it. It's closed under addition. It's closed under scalar multiplication. C1R, a subspace of CR. Well, but before you can answer that question, you got to know what these things are. CR, that's a little simpler. The vectors in there are really functions. And to emphasize that, in the lectures, I often call this a function space instead of a vector space. The elements, the points, are functions like, well, polynomials like t squared, but also functions like sine of t, cosine of t. Not natural log of t, because that's not defined in all of R. E to the t, e to the negative 5t, linear combinations of those things. Compositions of continuous functions are continuous. C means continuous. We're talking about all real valued functions whose domain is the entire real number line and which are continuous on the entire real number line. The vectors in this vector space are functions. On the other hand, C1, the one emphasizes those functions are not only continuous, but also differentiable and a little bit more. What's the little bit more? Their derivatives are continuous. Now you might ask, well, how could the derivative not be continuous? There are actually examples of functions that are differentiable having a derivative everywhere, but the derivative is not continuous. In fact, I'll show you a graph of one. They are very strange examples. The most prominent example I can think of is a piecewise function that's defined to be x squared times sine of 1 over x when x is not 0, and 0 if x is 0. You may note if you plot sine of 1 over x near 0, you get a graph that oscillates infinitely often. If you graph x times sine of 1 over x, well, it still oscillates infinitely often, but those oscillations get smaller and smaller, enough to make this limit exist as you approach 0. If you multiply it by x squared instead of x, they get smaller and smaller pretty rapidly. And if you make it piecewise by defining it to be 0 when x is 0, the graph's not going to change here. You actually come up with a differentiable function. This function is differentiable. In fact, you can even say what f prime of 0 is. It turns out to be 0. However, this is a big however, if you plot the derivative, you will see it's not a very nice function. it itself doesn't have a limit as x goes to 0. That's the graph of the derivative. Even though f prime of 0 is 0, that derivative is not a continuous function at 0. It does exist everywhere, but it's not defined at, it's not continuous at 0 because the limit doesn't even exist. Actually, I did allude to this in one of my lectures. So there are actually functions that are differentiable, but the derivative is not continuous. Anyway, that's not the main emphasis of what I'm trying to say here. C1 means derivative exists and is continuous everywhere. In fact, we got a name for that. That's called continuously differentiable. Something I emphasized when I talked about the linearization theorem. Yes, no, trick question, vice versa. Yeah, that's a yes. Every function whose derivative is continuous is also a continuous function. It's enough to know that this is a subset of this and that they are both vector spaces. You could use the subspace test if you want to be extra picky about it, but you'd really be verifying that this is a vector space to begin with. The 0 function is in there. The 0 function is the same as the 0 polynomial. Add 2 functions whose derivatives exist and are continuous. You'll get another function whose derivatives exist and is continuous. Multiply such a function by a scalar, you get another function whose derivative exists and is continuous. That takes proof. Proof based on limits in calculus, properties of limits. We're not proving those kinds of things in this class. That's not our main point. Our main point is just to see that these are vector spaces and related to what we're talking about with differential equations in linear algebra. And that comes up in number 4. If these are vector spaces, then we can define linear transformations between them. In this case, capital T is defined by this formula. Give me a function little f that is in here, continuously differentiable on the entire real number line, and map it to a function in here by taking its derivative and adding 4 times the function. This came up on the last exam. For example, t of sine of t, for example, would be take its derivative and get cosine of t, and then add 4 times the function. Capital T would map the sine function to this function, cosine t plus 4 sine t. It's a mapping. Is it a linear transformation? Yeah. How would you verify that? By proving it's operation preserving. That can actually be done in one step instead of 2 separate steps. Give me an arbitrary linear combination of 2 functions, little f and little g. So alpha and beta here are scalars, numbers. F and g are functions. That's understood. Plug that linear combination into this formula. That means I got to take the derivative of alpha f plus beta g, put a prime there, and then add 4 times that linear combination, like that. Again, it's understood when I write this. I'm saying it. Alpha and beta are scalars. F and g are continuously differentiable functions. I'm assuming that. Prime means derivative. 4 times this thing in parentheses is multiplication. Then use properties you know from calculus. You know that the derivative of a linear combination like this is alpha times the derivative of the first function plus beta times the derivative of the second function. You know that from calculus. You might just say we're being a little sloppier with our notation because I'm not bothering to write the of t's in there. That's understood that f and g are functions of, say, little t. I'm not even saying actually what the variable truly is here, but then use the distributive property, distribute the 4 through like this. Then it's a matter of just realizing what you need to do. You need to verify ultimately that this equals alpha times t of f plus beta times t of g. Now you could work backwards and figure out what that is first. But if you're skillful enough at this, you can realize what you need to do is you need to group the terms involving F together and the terms involving G together. And in both cases, factor out an alpha and then a beta from those. Using properties of algebra, you can rewrite this like this. And that is alpha times T of F plus beta times T of G. And that one line of equations actually is enough to prove operation preserving. You could separate it into two steps, prove capital T preserves addition and prove it preserves scalar multiplication, but it actually is good enough just to show this equals that. That's the equality we're trying to show ultimately. What's the kernel? All functions of the form, what? You're solving a differential equation to find the kernel. Setting that equal to 0. Answer involves E. If you guess something involving E, you're right. Well, you might be right. E to the negative 4t times an arbitrary constant. You could say the kernel, you're trying to solve the differential, this is related to differential equation. It's like dy dt plus 4y. And to find the kernel, we're setting it equal to 0 and trying to find y. That's equivalent to dy dt equals negative 4y. You could separate variables. That's simple enough. You could guess. We've talked about that kind of differential equation a lot. Arbitrary constant times e to the negative 4t. Usually we just write this as y equals that, right? And call it the general solution. It really is an infinite family of functions, though. One for each value of c. You could also use the span notation here. You could call this the span of e to the negative 4t. That's the way you could describe the kernel. Make sense? We're just trying to relate the differential equations ideas we've been talking about to linear algebra now, to the vector space stuff. They are related. And it does turn out to be a useful thing to relate them. Why, you might wonder. Let me see if I can hint at why. Let's bring dimension into the picture. The dimension of a vector space, well, if it's finite dimensional, it's the number of elements in any basis. If a vector space has got a finite basis, it will be finite dimensional, and any other basis will have the same number of vectors in it. Just as examples, R2 is 2-dimensional, R3 is 3-dimensional. Any vector space, by the way, with dimension bigger than 0 has infinitely many bases. Infinitely many bases, right? There's infinitely many bases of R2. Any two vectors that are not non-zero and not parallel are going to form a basis for R2. R3 is 3-dimensional. Any basis has 3 vectors in it. P2 is a vector space. All polynomials of degree less than or equal to 2. Careful, what's the dimension of P2? Is it 2? The answer is no. What is it? It's 3. Give me an example of a basis of P2 as a set of 3 polynomials. There's a real simple example. 1 T. Give me the third one. I say it in lectures. Nobody? Uh-oh, this is making me sad. T squared. Yeah, there we go. P2 is all polynomials of degree less than or equal to 2. An arbitrary such polynomial is of the form, say, a plus bt plus ct squared, a linear combination of the three polynomials 1t and t squared. And those polynomials turn out to be linearly independent as well. They do form a basis for P2. Any polynomial of degree less than or equal to 2, the fact that it can be written this way implies this set spans P2. It's also linearly independent. That's a little harder to think about, linear independence there. Don't have time to go into details. P3 is 4-dimensional. Add t cubed to get a basis of that one. But there are actually infinitely many bases of these things as well. These two vector spaces don't have finite bases. They are infinite dimensional. A little hint about why, think about C1. You know, any polynomials in there of arbitrary degree, that's enough to say it's infinite dimensional right there. The degree could be 2, 5, a million, a billion, a Google. Okay. Arbitrary degree, there's no finite basis for sure, just even based on that. But it's also got other functions like e to the t, e to the 2t, any exponential function, growth or decay, cosine t, sine t, linear combinations of those things, compositions of those functions, sine of e to the t, for example. It's an infinite dimensional vector space. That's infinite dimensional too. This kernel, though, is 1-dimensional. It's spanned by one quote-unquote vector, e to the negative 4t. That one vector, that one function is a basis for this subspace. The kernel is a subspace of C1. How do you prove that that's the answer? There's some theory you can do, and I don't really emphasize this enough in the lectures. I think I mentioned it once. There's some theory that you can do that says that first order linear differential equations have 1-dimensional kernels, if you think of them as linear transformations. So if you find one solution, one non-zero solution, it's automatically going to span, it's automatically going to be a basis. That fact right there is enough to justify our connections between the linear algebra and the differential equation right there. And it generalizes. I could come up with a second order differential equation, y f double prime plus f prime plus something, plus f, whatever. And think about the solution space for the corresponding homogeneous equation, the kernel of the corresponding linear transformation. You can do some theory and prove it's got to be a 2-dimensional vector space because it's a second order differential equation. So if you can find two linearly independent solutions, those solutions automatically have to span the space. You can get you can write down the general solution and know it's right. That kind of stuff is enough of a reason to justify doing the abstract linear algebra and relating these things. We're not fully doing all the theory. We're just touching on the theory and trying to see why the theory is worthwhile. If you were doing a more full linear algebra class, you go deeper into the theory, we'd do proofs of those facts that I just quoted, in fact. We don't have time for that. Class is hard enough as it is right now. Fifth problem is about finding a coordinate vector. Let's think about it a couple ways. There's, first of all, the definition of what a coordinate vector is. The coordinate vector of x relative to this basis, and this would be a basis of R2, the plane, because these are two vectors in R2 that are not parallel. is gonna be a vector in R2 as well. Call the components C1 and C2. You got to find those numbers. How are they defined? They are the weights in a linear combination like this, C1B1 plus C2B2, where you get X. Solve for those weights. Effectively, you got to solve a system of linear equations in the unknown C1 and C2, which can be done by row reduction. The components of the B vectors form the coefficients. We could make an augmented matrix with X on the left, and you could do row operations. Let's see, I'm going to multiply row 1 by -1 and add it to row 2. And this is what I would get. Then multiply row 2 by 1/2 and get this. Then add row 2 to row 1 to put the answer in row 1 and get your final matrix. Add row 2 to row 1. I'm going to get a 2 there. So C1 is 2 and C2 is 1. And that means, therefore, the coordinate vector of X relative to this basis is 2, 1. That's the answer. Another way to get the answer is to use what's called a change of coordinates matrix, traditionally called P, where you put the B vectors in the columns of P. So P equals 1, 1, -1, 1. And P does relate X to the coordinate vector of X relative to the basis, though in a way that's a little confusing. To get the coordinate vector, you might say the new coordinates of X. You don't multiply P times X, you multiply P inverse times X. So you got to find P inverse. Use the shortcut formula, take 1 over the determinant of P. The determinant's going to be 1 minus -1, which is 1 plus 1 is 2. Swap the entries on the upper left and lower right. They're both 1, so they stay both 1. Negate the entries on the off diagonal. Somebody have a question? You can multiply the 1/2 times every entry here. I think I'll just go ahead and multiply the matrix times the vector and leave the 1/2 in front here at first. 1 times 1 plus 1 times 3 is 1 plus 3 is 4. And then the other one's going to be -1 plus 3. Multiply each component by 1/2, you get 2, 1, you get the same answer. This change of coordinates matrix is going to be a big deal for us in chapter 3 of the textbook, when we relate what's going on with the differential equations to linear algebra. When we talk about the eigenvalues and eigenvectors, this is going to be a big deal.